This video will help us practice two important ideas. First of all, the concept of the dot product. Second of all, how to set up a proof. Here's the problem. Let u and v be two vectors in R2. We want to show that u dot v is equal to v dot u. Anytime you want to show that one thing is equal to another thing, the idea is to start with the more complicated side and turn it into the other side step by step. Now, in this case, neither of these expressions here, u dot v nor v dot u, neither one is more complicated than the other. So I would say it would be more natural to start with the left side. I'm going to write u dot v on the left side here, and we're going to show step by step that u dot v is equal to something, which in turn is equal to something else. And gradually we're going to get down to the bottom here and we're going to be able to show that that is equal to v dot u. So we're going to show that the left side is equal to the right side. That is what I consider the basic setup of the proof. Now this is where it would be easy to get stuck. We need more detail in order to complete this proof. We were told that u and v are vectors in R2, so we know that each vector has two components. And we want the proof to be general, meaning we want this to work for any choice of u and v in R2. So what we actually need to say at the beginning here is something like, let u equal, and we need to give names to its components. Let's call it u1 and u2. Those are our components of u. And we'll say similarly v is equal to the vector v1, v2. That way now we've got the detail that we need to complete the proof. So let's start on our proof. U dot v is equal to, well, by definition of the dot product, we are multiplying the first components of the two vectors, so u1 times v1, and we're adding that to the product of the second components. So u dot v is equal to u1 v1 plus u2 v2. If you want, in brackets at the side here, you can justify this step. I'm just going to write quickly definition of the dot product as the justification here, just so that we can follow along. Let's say that justification there is optional. All right, now next step. Looking at where we're trying to go, we're trying to produce something that looks like v dot u. So at some point, the order has to be rearranged here. Let's think about whether it's valid to take this expression u1 v1 plus u2 v2 and say that it's equal to v1 u1 plus v2 u2. Well, in fact, yes, these two things are equal because u1, v1, u2, and v2 are all just real numbers. So we're just using properties of the real numbers here. Now over on the side, I'm just going to scribble something here. Let's put in some real numbers here. Let's say u1 is 2, v1 is 3, u2 is 4, and v2 is 7, for example. So all we're saying in this step here is that if we were to take 2 times 3 plus 4 times 7, that is the same thing as 3 times 2 plus 7 times 4. It just goes back to basic properties of the real numbers. Now continuing our proof, we've got v1 u1 plus v2 u2, and we eventually want to show that this is equal to v dot u. Now all we need is one final step to connect these quantities. I'm going to erase this dot dot dot, and I'm going to write in here, well, again using the definition of the dot product, v1 u1 plus v2 u2 is exactly how v dot u is defined. So we've shown that u dot v is equal to v dot u for any choice of vectors u and v in R2.